In the previous video, we defined a vector field simply as a function defined on some region in the plane or in 3 space, which associated to each point some vector. In the examples that we looked at, the vector was just a formula that was given with no indication of where it came from. So in this video, we're going to look at a particular type of vector field that comes from a multivariable function, and that it turns out to be very, very important in vector analysis. So if I have a function, a multivariable function with two variables, so let's say that I have a function z equals f of x and y, well then I know its gradient vector is a vector function where the component functions are f sub x and f sub y, right, the partial derivatives with respect to x and y respectively. And this is a function that takes as its input a point x, y and outputs a vector. And so this is a vector field. In this case on R2 or on some region of R2. And it's called the gradient vector field. So for each two-variable function f, we have a gradient vector field defined using the gradient of that multivariable function. Similarly, if I have a function w, which is a function of x, y, and z, so a three-variable function, right, then the gradient vector, f of x, y, z, which is defined by the partials with respect to x, y, and z. Right, is a vector field on R3. And again, called a gradient vector field. So each three-variable function f gives a vector field on R3. So let's take a look at an example. So if I start with some two-variable function, let's say f of x, y equals x squared y minus y cubed. Right, this is a nice two-variable function. Right. We can easily compute its gradient vector. So the partial with respect to x is going to be 2xy. And the partial with respect to y is going to be x squared minus 3y squared. And so this is a formula for our vector field, for our gradient vector field. For any point in the plane x, y, we can compute this vector, and then if we wanted to, we could draw a vector or an arrow in the plane pointing in the indicated direction with the given magnitude. And here's an image of this particular vector field with the arrows in red. Notice that some of the arrows are pointing towards the origin, some of the arrows are pointing away. It really depends on the location of the point. Now also in this image are some of the level curves of this particular function. So these were formed by setting the function f of x, y equal to certain constants and drawing those constants in the plane. Now what you'll notice is that every time one of these arrows intersects one of these level curves in the plane, that relationship is orthogonal. So this vector field is orthogonal to all of the level curves in the plane. One question that is often important to determine about a vector field in many applications is whether or not it is the gradient vector field for some function f. And so in order to deal with this nicely, we're going to give this a name. And so we're going to say that a vector field f is conservative if capital F is equal to the gradient of a function lowercase f for some function f. So in this case, if this is the case, then lowercase f is called a potential function. For our vector field. This turns out to be one of the most important, if not the most important, property of a vector field, the property that a vector field can have. And so we'll eventually come up with a way to really quickly determine whether or not a vector field is conservative, and then in the case that it is conservative, come up with a procedure for finding the potential function. However, for now, we'll just want to look at a couple quick examples of this. So let's say I have a vector field defined on the plane given by this formula. So the first scalar field is going to be 12xy, and the second scalar field is going to be 6x squared plus 2. All right, and the question we have here is this vector field conservative or not? Now, if we look at it, we don't really have anything other than this definition, so the question just simply, is this the gradient vector for some function? And so if we just kind of play around with it, we could probably come up with eventually that if we take the function f of xy equals 6x squared y plus 2y, then we see that this is in fact the gradient of this function f. Right? So this was, at this point, we just kind of looked at it and thought about how partial derivatives work, and we're able to just write down the function. And once we have this potential function, we can quite easily show this is the gradient vector just by finding the partial derivatives. But in this case, coming up with this function does tell me that this function is conservative. Right. Now in this case, we only were able to do this because I was able to write down a potential function f just by observation. But like I said, we will come back and look at a more systematic approach to this later once we have some more machinery at our disposal. I also want to look at this particular vector field. We've seen this one before. So the vector field is going to be negative y and x. This was the first example of a vector field we saw in a previous video. And so we could also ask the same question here. Is this vector field conservative? And in order to, if the answer is yes, in order to show that, we just need to write down a potential function. And if the answer is no, we have to sort of explain why. And this is where it gets a little bit dicey because we don't have any machinery right now. It's really difficult to show that this is not the gradient for some function, because we'd have to show for every single multivariable function out there, we do not get this vector as a gradient for any of them. And the answer to this is that this turns out to be something that is not conservative. And we don't have the machinery right now to verify this, but it's pretty clear if you just try to write down some examples that satisfy both of the partial derivatives being equal to negative y and x respectively, that it's really just impossible to do. But of course that doesn't justify anything. But we will have a really clean way of showing that these two examples are conservative and not conservative respectively.